Happy New Year and welcome back to Hypnosphere. Find a quiet place, let your shoulders soften, and let your breath fall into a gentle rhythm. This is a space for unhurried science, a place to learn with your eyes half closed, where curiosity moves at the pace of a resting heartbeat. Tonight, we are traveling back to a time when the map of the planet was almost simple. Not many countries, not many continents. Just one land, broad and continuous, cupped by a single world-spanning ocean. That land was called Pangea. You can imagine it like a vast continent-scale plain of stone that folded and lifted into mountain ranges, then fell away toward a rim of coasts and cliffs. It stretched from pole to pole. It connected the pieces that we now know as the Americas, Africa, Europe, Asia, and Australia. Around it spread Panthalassa, the great ocean that wrapped the globe like a dark, moving blanket. Along one arc of shoreline lay the Tethys, a warm, shallow sea full of reefs and lagoons, a ribbon of blue along a shoulder of the supercontinent. Pangea was not a moment. It was an era of arrangement. It assembled over millions of years and held its shape, more or less, between about 335 and 175 million years ago. That window spans late Carboniferous forests, Permian deserts, and Triassic recoveries, a sweep in which life learned, lost, and tried again. If you look at a globe today, the continents feel like islands of meaning, each with its own climates, its own winds and rains. Pangea was different. It had a single immense interior. The supercontinent effect made the heart of the land dry and extreme, far from any ocean's gentle breath. The coasts received rains in rhythmic seasons, while the inland basins baked, then chilled, under open sky. Picture a year that arrived not in dates, but in pulses. In summer, sunlit heat built over stone and sand, drawing air upward, creating a low-pressure breath that pulled sea air landward. Storm belts formed. Rivers swelled along the edges. In winter, the process reversed. Winds blew outward from the cooling continent, clear and dry, leaving salt flats and parched soils. Geologists call it a megamonsoon, not because storms were fierce in every moment, but because the entire planet's air seemed to move with the slow in-out of a single giant landscape. On the ground, this created worlds within a world. Along the Tethys, you would find warm shoals, reefs built by sponges and early corals, and coastlines dotted with lagoons that salted out under a long sun. Move inland, and the land blushed red with oxidized iron in the soils, a memory of long dryness. Sand seas lay in belts, especially as the supercontinent aged and the later Triassic approached. Between deserts, there were basins that pooled with seasonal lakes. They were lined with mud that cracked into tidy polygons, then softened again under rain. These basins preserved the footfalls of animals we sometimes think of as mythic because we meet them first in museums. Early relatives of mammals, with sturdy bodies and beak-like mouths. Lizard-hipped and bird-hipped dinosaurs, not yet rulers of the land, moving among conifers, cycads, and ginkgo-like trees. Insects sang from low shrubs and rushes along oxbow lakes. Dragonfly relatives with wide wings sketched slow arcs over water that smelled faintly of resin and clay. It is easy to imagine that such a world would have felt alien, but much of it would feel strangely familiar. A breeze is still a breeze, no matter the age. The hush under conifer needles is the same hush that might cradle you on a walk today. The sun would slide low and change the color of stones in a way that your eyes would recognize. Even the stars, once the sky cleared, would map their old slow wheel. The day, however, would be a little shorter. Deep time studies of growth bands in ancient corals tell us that hundreds of millions of years ago, the Earth rotated faster than it does now. In the Permian and Triassic, a day may have been closer to 22 or 23 hours long, and there were more days in a year. The moon was a little nearer, the tides a little stronger, and the planet's rhythm a fraction brisker. When we ask what Earth was like during Pangea, we are asking many questions at once. What did the air feel like? How did rain travel? Where did forests grow? And what did animals do with their days? How did oceans move around a supercontinent? And how did those currents shape life? How did volcanoes write heat into the sky? And how did life respond? We also ask a human question. What does it mean to live on a planet that rearranges itself with patient certainty? What does it teach us that land can break, drift, collide, and breathe in new configurations, all while life quietly adapts? If you would like to share, tell us where you are listening from and what time it is for you. A city window at 11 p.m., a countryside porch at dawn, a long commute under a slow rain. Knowing that others are hearing the same story from different edges of the modern map brings a gentle echo of that ancient unity. Tonight, we will walk through Pangea with calm steps. We will listen to the science and to the steady patience of the earth. We will begin by looking at how we came to know that Pangea was real. Then we will move through climate and life, through rivers and reefs, through deserts and polar forests, and we will try to feel, in a small human way, what that world was like. Let your breath settle as we cross the threshold. The first clues were not in computers or satellites, but in rocks and in the quiet matching of patterns across oceans that did not yet exist. Long before we could measure the seafloor or model global winds, humans noticed that certain pieces of the world seemed to belong together. The curve of Brazil looked like it might nest into the Gulf of Guinea. Fossils found in South America matched fossils in Africa. Rocks in Scotland seemed to continue in Newfoundland. These were observations like seams in an old quilt, visible if you look with soft eyes. In the early 20th century, a German meteorologist named Alfred Wegener gathered these clues with patient care. He proposed that the continents were once joined in a single mass, which he called Pangea, and that they had drifted apart over time. At first, many geologists resisted. There was no known engine powerful enough to shove whole continents around. But the pattern of evidence was undeniable. Small freshwater reptiles called Mesosaurus left bones in both Brazil and South Africa, far too delicate to have crossed an entire ocean. Fern-like plants called Glossopteris appeared across what are now India, Australia, South America, and Antarctica, suggesting that those lands once shared a climate and a connected ecosystem. And there were ancient scratches and grooves carved by glaciers in bedrock from South Africa to South America and India, pointing in directions that only make sense if those lands were once attached and lay closer to the pole. Geologists added other clues. Mountain belts on either side of the Atlantic line up when you move the continents together in your mind. The Appalachians in North America match the Caledonian and Variscan mountains of Europe and the ranges in Morocco. These are not coincidences. They are the scars of a collision, the stitches that formed when pieces of old crust pressed together in rows. The match is so tight that you can trace ancient belts of metamorphic rocks across what are now oceans. In the quiet language of stone, the lands tell you they were once one. Climate clues gathered in quiet layers. Coal beds, made of ancient swamp forests, appear not only in warm regions, but in places that are now cold, such as the Arctic islands and Antarctica. This does not mean those places were always warm. It means that the land that now sits in polar light once stood nearer to the equator, thick with swamps. Sandstone stained a deep red, called red beds, hold the cross-bedded signatures of ancient dunes and river floods. Their color and structure tell of oxidizing, sunlit, seasonally dry surfaces. Thick stacks of evaporites, such as halite and gypsum, testify to long, hot seasons where shallow waters were isolated and slowly evaporated, leaving salt behind in rhythmic beds. Put these together, and you see a map of climate that is different from today's, yet clearly organized by the shape of a giant landmass. Wegener's insight needed a mechanism, and that would come later. In the mid-20th century, after the Second World War, ships with magnetometers began to map magnetic stripes on the seafloor. These stripes recorded reversals of Earth's magnetic field, frozen into basalt as it cooled. The pattern was symmetric around mid-ocean ridges, showing that new crust formed there and spread outward. This was the engine that had been missing. The ocean floors were not ancient and static. They were born along ridges and consumed in trenches. Continents moved, rafted along by deeper currents in the mantle. With this, the idea of Pangea snapped into focus, not as an imaginative fit, but as a testable reconstruction. As Pangea assembled, the continents that would become North America, Europe, and parts of Asia fused with Gondwana, the southern supercontinent of Africa, South America, India, Australia, and Antarctica. The collision created a mountain spine near the equator, sometimes called the Central Pangean Mountains. These highlands shaped wind and rain. Air lifted over them, cooled, and dropped moisture on one side, leaving a rain shadow on the other. Long river systems flowed off those ranges into deep basins, carrying silt and sand that would later cement into red beds. In some basins, ancient lakes rose and fell with the seasonal cadence of the monsoon. Fine layers of mud, laid down year by year, preserved the rhythm of wet and dry like a long, thin metronome in stone. The animals that walked under this sky were not the dinosaurs of popular imagination, at least not at first. During the early Permian, the land was dominated by synapsids, the distant relatives of mammals. Creatures like Dimetrodon, with a tall sail supported by elongated spines, hunted fish-filled rivers, and low floodplains. Later, therapsids, a group that includes the ancestors of mammals, spread into many niches. Some were nimble insect eaters, some were heavy and slow, feeding on tough plants. Plant communities were changing too. Earlier, in the late Carboniferous, swamp forests thick with giant horsetails and seed ferns had fixed vast amounts of carbon, raising oxygen levels in the air and laying down thick coal. By the Permian, as the climate dried in many regions, these swamp forests retreated. Conifers and other seed plants that tolerated drier conditions spread. Insects adapted, some of them impressively large in earlier times when oxygen was high. Dragonfly relatives with wingspans as wide as your arm traced routes along water. The chorus of crickets and cicadas, already ancient as a style of sound, would have been a familiar texture to the ear. Along the margins of Pangea, Panthalassa rolled, and on one long arc the Tethys Sea offered warm shallows. Reefs breathed and built, made by organisms that looked different from modern reef builders, but played a similar ecological role. Onshore, tidal flats preserved ripple marks, rain prints, and trackways, the small, quiet signatures of a day's passing. If you stood there in late afternoon, watching thin clouds drift in from the sea, you might have felt the first drops begin to patter on a ground that smelled of salt and resin. Far inland, the same drops would not come. There, under a high sun in a pale sky, the wind would have tasted of dust. As we try to feel this world, it helps to return to that gentle idea of a planet breathing. When a landmass gets this large, the seasons of wind become a slow tide of air. In the wet months, the edges drew in moisture and poured it over river basins. In the dry, the continent exhaled. For life, this predictable rhythm was a guide. Trees set buds to match it. Animals tracked resources as the rains moved and retreated. The earth was not setting a drama. It was setting a pattern. And within patterns, life finds a way to make meaning. In the next part, we will look more closely at how scientists have reconstructed the fine details of that pattern, using magnetism in stones, chemistry in ancient air bubbles, and the layered stories written in varied soils and lake muds. Slowly, we will let the science draw lines on our mental map until we can walk across Pangea with more confidence, step by step. To understand the climate of Pangea, scientists reached for tools that read the past without disturbing it. One of the most elegant is paleomagnetism, the study of the magnetism recorded in rocks as they form. When lava cools or sediments settle, tiny mineral grains act like a million small compasses. They align with Earth's magnetic field and freeze in place. Later, even after continents wander, those tiny compasses still point in the direction of the field at the time and place of their birth. By measuring the direction and inclination of magnetization in rocks of different ages from different parts of the world, geophysicists can trace apparent polar wander paths. When the paths from different continents are brought together, they line up only if the continents are rotated and moved into their ancient positions. This is one way we know how Pangea was arranged through time, how it drifted slightly, and how it began to break apart. Another quiet archive comes from the chemistry of carbon and oxygen in shells, limestones, and even in the tiny pores of fossil leaves. The ratio of heavier to lighter oxygen isotopes in marine carbonates can reflect temperature and the volume of ice on land. Carbon isotopes tell stories about how much organic carbon was buried, which influences oxygen levels in the air. Stomatal density in fossil leaves, the count of the tiny pores that plants use to breathe, changes with the concentration of carbon dioxide. When CO2 is high, plants need fewer pores. When it is low, they open more gates. By comparing ancient leaves to living relatives, researchers have estimated swings in CO2 across the late Paleozoic and early Mesozoic. During the late Carboniferous, CO2 fell as lush swamp forests buried carbon in thick peats. This likely helped drive an ice age in Gondwana, with glaciers spreading across parts of what is now South America, Southern Africa, India, and Antarctica. As Pangea matured into the Permian and Triassic, CO2 rose again. The climate warmed, and the interior dried. Charcoal is another soft-spoken witness. Fire needs fuel, a spark, and oxygen. In periods when oxygen in the atmosphere was higher than today, fires could start more easily and burn more intensely. Thin layers of fossil charcoal in rocks tell us that wildfires were common in some times during Pangea's history. In the early Permian, when oxygen was still elevated from the Carboniferous peak, fires probably ran through dry seasons in pine-like forests, the air scented with smoke and resin. Later, as oxygen dropped toward more modern levels, fires remained part of the landscape, especially near seasonally dry coasts, but their character shifted. You can imagine the way regional fire patterns knit into the monsoon rhythm, clearing space for new growth during the dry breath, and seeding the land with ash that fed tender shoots when the rains returned. Wind patterns have been modeled using the shape of Pangea as a boundary condition. Climate simulations, checked against the sediments we actually find, show the signature of a global-scale monsoon. Along the western coasts of the supercontinent, where oceanic air had to cross broad tracts of land to reach the interior, rain fell seasonally and heavily. Along the equatorial belt, near the central Pangean mountains, uplift squeezed out storm bands and fed long rivers. In the deep interior, high-pressure systems parked their stillness under clear skies. Evaporation was strong, and little of that moisture returned as rain. In some basins, this dryness left behind dunes whose cross-bedded angles still stand today as stone. In others, ephemeral lakes formed, their margins gathering mud that cracked into neat tiles and preserved the delicate prints of animals and raindrops. The ancient oceans responded to this geography in kind. Panthalassa covered more than half the earth, and its currents were shaped by a very different arrangement of continents. Instead of many choke points and gyres like today, Panthalassa hosted long, sweeping flows. Upwelling zones brought nutrients to the surface, feeding plankton blooms that drifted through broad lanes of water. The Tethys Sea, a warm and shallow embayment, was a cradle for reefs and a corridor for marine life. Ammonoids, with their coiled shells, were common and diverse, rebounding after environmental crises with remarkable speed. Fish swam in many forms, from sharks with graceful tails to coelacanths that beat archaic fins through clear water. On some coasts, tidal flats recorded the slow rise and fall of the moon's pull in mud and ripple stone, like a finger tracing a soft line in wet sand. There were hardships for life. The end of the Permian brought the most severe mass extinction in the fossil record. It was likely driven by a cascade of events linked to enormous volcanic eruptions in what is now Siberia. Basalts poured out for hundreds of thousands of years, releasing gases that warmed the planet and altered ocean chemistry. Warming reduces the ability of water to hold oxygen. Nutrient changes can trigger blooms that use up what oxygen remains. Parts of the ocean slipped into anoxic and even sulfatic states. On land, acid rain and fast warming stressed forests. Yet even as we acknowledge this, we can hold the tone gently. Life did not stop. It thinned and reorganized. In the earliest Triassic, small animals like Lystrosaurus, a sturdy, tusked plant-eater, wandered floodplains in great numbers. Reefs rebuilt, this time with new coral groups. Archosaurs diversified, giving rise to crocodile relatives, pterosaurs, and the first dinosaurs. The earth kept breathing. A monsoon returned. Trees set buds again. In the rhythms of light, there were other subtle differences from today. Fossil corals and shells hold daily and seasonal rings that reflect growth. From these, scientists infer that days were shorter during Pangea's time, and years held more days. This is a natural outcome of tidal interactions between Earth and Moon. The Moon, raised a little higher in the sky than now, and a touch larger to the eye, would have made some high tides higher and some low tides lower, in patterns that repeated in steady cycles. Nights near the poles would have been long in winter, but even there, fossil wood tells us that forests stood, adapted to low-angle light and long dormancies. Rings in their trunks record seasons within the supercontinent's larger seasonal breath. When science sits quietly with these many threads and brings them together, Pangea becomes more than a map. It becomes a lived pattern, a climate machine with a particular tune. It becomes a set of roots and barriers that life worked with and around. In the next part, we will take those patterns and walk them, gently, with images that settle into the mind. We will cross from coast to interior, from equator to pole, and we will let analogies help us feel distances and times that our bodies cannot literally hold. We will think of winds as music, of deserts as the open pauses between notes, and of mountain ranges as deep chords that shape the song. Picture yourself at dawn on the shore of the Tethys Sea. The water is warm at your ankles, and a chorus of small waves taps the strand line. The air smells faintly of salt and something floral from the low coastal scrub. To your right, in the hazy distance, a line of reefs gathers the incoming swell and breaks it into lace. The creatures that build these reefs do not look exactly like modern corals, but they make the same kind of complicated neighborhoods, full of niches and shade, edges and shelters. Fish idle in the calm. Ammonoids glide in slow spirals, their shells holding a precise geometry of chambers that they fill with gas and liquid to control buoyancy. A small pterosaur lifts from a rocky perch with a careful push, its wings taut and silent. On this coast, the day opens gently, and you can feel the planet invite warmth. The wet season is beginning. Clouds are forming in long ranks offshore, and the first rumble of a morning storm arrives like a drumbeat from over the horizon. If you begin to walk inland, the world changes with a steady cadence. The shore gives way to tidal flats, then to lowlands patterned by distributary channels. Here, the ground is a mosaic. Patches of sand, tongues of silt, and islands of vegetation braid together. Plants hold on to the banks. Small, upright conifers cast fine shade. Ferns fill the gaps. In the wet months, rain grids the surface with ripples and overflows. Fish and amphibians move into temporary pools. In the dry months, water retreats and leaves behind cracked mud. The air grows resinous. Fires sweep gently through, low and fast, tiding rather than destroying. Tracks of early archosaurs and synapsids stitch lines across damp ground. A footprint is a moment of wait, preserved when the next storm lays a thin film of silt over it like a blanket. A day's walk farther, and the land becomes more open. The sky feels larger. Rolling uplands give way to plateaus, then to the outwash plains of a mountain spine. The central Pangean highlands are not a single ridge, but a complex of raised country. They gather air like a hand lifting a veil. As that air rises, it cools. Rains spill down one side, interrupting the day with showers that drum on leaves and fill gullies with laughter. On the other side, in their long-range shadow, you step into the slow hush of the interior. The land blushes red from iron in the soils. Pebbles glue into conglomerates along old riverbeds. Dunes form, not all at once, but in increments. Gentle winds draw lines on the sand. Each grain is a small traveler with a story of knocks and rests. When we see crossbeds in a sandstone today, we are looking at the fixed pattern of those movements, the memory of millions of gentle slides and falls. Deserts in Pangea's interior were not empty. They were quiet in a stocked way. Burrowing animals spent the heat of day in the cool beneath. Tough shrubs and conifers spaced themselves like careful notes in a wide score. When rains came, they did not always come hard. Sometimes they arrived as an afternoon blessing, a scent lifted from dust, a spreading dampness that the land drank with gratitude. In low places, lakes would fill. Some were salty from repeated evaporation. Some were fresh and briefly generous. Around them, life gathered. Bones weathered and left their phosphorus to the soil. Logs drifted in and became the seeds of petrified wood, slowly trading cell by cell for minerals that would keep their form. The dusk here was a long decline of heat. Stars appeared early. Constellations not yet named by any human mind rose and tilted. If you turned northward, you would eventually reach latitudes where summers were long and bright, and winters were long and dim. Permian and Triassic polar forests adapted with patience. Trees grew slowly and then very quickly, laying down wide rings in the light season and thin rings as they slept. Understory plants waited for the returning sun with a kind of vegetal memory. Animal life here moved with the seasons. Some likely migrated, following the edge of warmth and daylight. Others settled and endured. The soundscape changed. Fewer cicadas, more wind in needles, a creak of iced branches on the coldest days. Yet even here, the earth did not feel hostile. It felt deliberate. A planet is not a person, but it behaves with a kind of strict kindness. It repeats what works. It builds on patterns. Across all this, the megamonsoon was the backbeat. Think of it as a slow music, a rise and fall that organized a year. Along the coasts, rains arrived predictably with the onshore flow. Rivers braided and unbraided. Estuaries widened and narrowed with the tides. Inland, the dry breath spread under a high sun, then yielded when pressure fell and winds shifted. For people living now, monsoons mean particular places, but in Pangea, the scale was continental. The concept remains the same. The position of the sun through the year warms land and water differently. The land responds quickly, the ocean more slowly. Pressure differences move air. Air carries moisture. Moisture rains or does not. If you hold this in mind, you can imagine yourself anywhere on Pangea and feel the air with a small, reasoned confidence. Life arranged itself along that pattern. In the wake of the Permian die-off, communities reassembled like a careful garden. Early Triassic floodplains often held small, hardy plants and herds of Lystrosaurus. Over time, ecosystems grew more complex again. Crocodile-lined archosaurs stationed themselves along rivers. Phytosaurs, with long, toothy snouts, slid into the water and waded in the shallows. Early dinosaurs, light and quick, threaded between shrubs and conifers, their steps writing calligraphy on soft ground. Mammal ancestors developed keen senses, a trait that would carry forward into the night worlds of later ages. Insects threaded everything together, as they always have, acting as pollinators and prey, recyclers and signalers. Their wings chattered in the heat and fell silent in the evenings when the first cool air drifted downslope from higher ground. In the sea, reefs rested and rose again. Before the Permian crisis, reef systems were made by different builders than today. Afterward, new coral groups took on the role of architects and created great limestone cities that stretched along the Tethys margin. In Panthalassa, slower, deeper currents carried nutrients and larvae across spaces that seem immense to us now. You can imagine a small ammonoid drifting in the lee of a floating log, shadow and company in a big water world. The log gathers life, worm tubes and filter feeders, little fish and crabs. In this way, even the open ocean had islands of structure. As Pangea aged, it began to rift. The crust thinned along new lines, and valleys formed that would later widen into oceans. The first signs were subtle, localized volcanism and linear basins that filled with sediments. These rifts often captured lakes that recorded climate in thin, annual layers. To stand on such a rift margin was to feel a long, slow future pressing outward. But while that future waited, the present remained stable to any creature's lifetime. Animals raised young. Trees dropped cones. The tides came and went. It is a helpful reminder that planets can change in two tempos at once, the human scale rhythm of days and seasons, and the deep tempo of plates and continents. Both were true on Pangea. Both are true now. When you hold these images together, you get a sense for the answer to the question that brought us here. What was Earth like during Pangea? It was a place of vastness, made intimate by repeated patterns. It was more extreme in its interior, and more predictable along its edges. It was a continent that taught the air to move with a wide breath, and an ocean that learned to sweep around a single mass. It was familiar and strange at once. In the next part, we will let that understanding settle into meaning. We will ask what this supercontinent teaches us about our own moment, about climate as a system that responds to shape and sunlight, and about the human gift of living in long stories that began before us and will continue after. Close your eyes for a moment and imagine the map of Earth without lines, without names, just colors of land and water. Let the continents flow together until they touch, until the saw teeth of one coast fit into the curvature of another. That is a gesture that mirrors deep time. Pangea teaches us that the planet is not fixed. It is dynamic in slow motion. The shape of continents is part of climate, and climate is part of life, and life feeds back into climate and stone. The breath of the earth is a conversation between rock and air and sunlit water. When we think about our own lives within this, it can be strangely relieving. We live in what can feel like a tight present, but the world's story is long, and that length can make space in the mind. When Pangea existed, the air held different balances of gases. Oxygen rose in certain periods, then declined toward levels we would recognize. Carbon dioxide fell as lush forests buried carbon, then rose again as volcanoes exhaled and as dryland spread. The planet cooled and warmed, and winds rearranged. With each change, life adapted. Sometimes the changes were stressful and rapid in geologic terms. Sometimes they were graceful and slow. Through all of it, the processes were connected. Plants shaped air, air shaped water, water shaped stone. Stone shaped wind and rain. There is a calm truth in that mutual shaping. It says that Earth is a system that seeks patterns, and that those patterns can be understood. Understanding Pangea also refrains our sense of distance. Today, we think of the Atlantic as a deep divide. In Pangea's time, that divide did not exist. Animals could, in principle, walk from what is now New York to what is now Morocco through a continuity of hills, rivers, and forests. Plants spread across vast ranges without needing to hitch a ride on currents. This does not mean that Pangea was uniform. Far from it. It contained many climates and habitats, some lush, some stark. But it tells us that connection is normal for life. When barriers are low, communities mingle and biodiversify. When barriers rise, communities specialize and diverge. The supercontinent gave a long lesson in both movements at once. There is a personal echo to that. We live on a single planet. We always have. The borders we draw are practical and cultural, and they matter for our human stories. But when we step back to the scale of deep time, we return to the feeling of one world. On a night walk, when you hear the breeze and see the moon, you are not so far from a Permian evening. The same physics shapes air and light. On a hot summer day, When the smell of warm pine comes into your car through an open window, you are smelling something that ancient animals also smelled. When rain hits a dry path and lifts that first mineral scent, you are sharing a sensation that happened on the shores of the Tethys and the edges of Panthalassa. Pangea is not just a science story. It is a way to place ourselves gently in the continuity of Earth. There are, of course, lessons for the present. The geometry of land affects climate. When large areas of land sit far from the sea, they become more extreme, with hotter summers and colder winters, and they dry if the winds do not bring rain. When continents drift, currents change, and with them the distribution of heat and nutrients in the ocean. These are not just curiosities. They are parts of the reason for the ice ages, for the rise and fall of sea level, for the growth and retreat of reefs, for the regional differences we experience today. Studying Pangea helps scientists tune the models that we use to understand modern climate, because it gives us a natural experiment. It tells us how the system behaves under a different arrangement of continents and a different balance of gases. When we get the Pangea puzzle right and the rocks and models agree, we earn a quiet confidence that we can trust these tools when we ask about our own future. There is also humility in it. No species in the Permian knew that the supercontinent would one day split, that a new ocean would open, that the Atlantic would widen like a slowly drawn curtain. No creature measured the day and noticed it getting longer by minutes across millions of years. Yet these changes happened. They were slow, which meant that local experiences were stable enough for life to go on. Parents raised young. Communities adapted. Rivers kept their songs. The slow changes set a stage, and life wrote its local plays upon it. Our species is unusual in that we can sense the long stage while we live our short plays. If we let that awareness be calming rather than alarming, it can make our days feel held within something steady. So if someone asks you what Earth was like during Pangea, you can answer softly. It was a single land that taught the air to move in great, seasonal breaths. It had coasts of warm lagoons and inland seas that dried, leaving salt and story. It had deserts that were quiet and stocked with life, forests that waited out long winters at the poles, and mountains that set the rain in motion. Its oceans moved in broad streams around a continent that reached from pole to pole. Its life changed, suffered, recovered, and diversified again. The days were a touch shorter. The moon was a touch nearer. The stars were the same. If you walked there at dusk, the world would smell familiar. Thank you for spending this time in deep time, listening for the Earth's slow music. If this gentle journey helped you rest and wonder, you are welcome to stay close. You can subscribe to Hypnosphere for more calm, curiosity-driven science stories. No hurry. We will be here when you are ready, breathing with the planet and wandering through its quiet, beautiful past.